In this video, we are going to discuss about binary codes. Binary codes are basically classified into three types: numeric codes, alphanumeric codes, and error reduction codes. Numeric codes is further classified into two types: weighted codes and non-weighted codes. The examples for weighted codes are BCD, that is 8421 code, then 2421 code, 5421 code, 84 -2 -1 code, and biquinary code, 1 out of 10 code. Similarly, the examples for non-weighted codes are XS3 and gray. Examples for alphanumeric codes are EBCDIC and ASCII code. For error reduction codes, we can have parity code as the example. Weighted codes and non-weighted codes are used to represent the decimal numbers, means only numeric data, whereas alphanumeric codes are used to represent the numeric as well as non-numeric data. Non-numeric data examples, your alphabets and non-printable characters also. And the foremost example for the numeric code, that is weighted code, is BCD code. BCD has 0 to 9 numbers, binary coded decimal. Okay. And it will be represented by 4 bit. Otherwise, it is called as 8421 code. For example, if I take 937.25, the decimal number, then how to represent in BCD is 9 has to be represented by 8421, that is 1001. Then for 3 it is 0011. For 7 it is 0111, and for 2 it is 0010. For 5 it is 0101. So just combining all and writing, you will be getting this answer: 10010011 dot 001000101. Similarly, we can have another example, 854. So 8 has to be represented as 1000, and this 5 can be represented as 0101, and 4 is represented as 0100. Similarly, we have other types of weighted codes: 5421, 2421, and 84 -2 -1. So as you notice, it need not be positive weights, it can be negative weights also. For example, if I in 84 -2 -1 code, I want to represent 1 means, then 4 -2 -1. So 0, 1, 1, 1. Similarly, if I want 2 means 4 -2 is 2. If I take 9, 9 is 8 plus 4, 12. 12 minus 2 is 10. 10 minus 1 is 9. So 1, 1, 1, 1. Similarly, any number we can represent. So another example is this 2421 code. In this 2421 code, after 4, if I want to represent 5 means, I will be using this 2. So 2 plus 2 plus 1. So 1011. And another code is 6, that is 1100, because 2 plus 4. So once you started using this 2 which is in MSB part, then we will be using that 2 for all. Similarly, another code is 5421 code. So this 2421 code is a self-complementing code, means the first number and the last number are nines complement of each other. For example, if you see here, for 0 it is 0000, for 9 it is 1111. That is the ones complement of each other. Similarly, for 1 0001, and for 8 it is 1110. That is the complement of each other. As if we have a complementing mirror after 4. So this for 5 it is 1011, for 4 it is 0100, complement of each other. Similarly, if I go for this 84 -2 -1 code, that is also a self-complementing code. The first number 000, last number 111. For 1 it is 0111. Here for 8 it is 1000. Likewise, all the numbers are just complement of each other. First half is the complement of the second half. Then another code, weighted code is biquinary code. That is a 7-bit code 5043210. So as you see here, each digit has 2 1s and 5 zeros. Okay. So if I want to represent, for example, 7 means, then 5 plus 2 is 7. I will be putting like this. For 0, there are 2 zeros are there. So we can put 1 there. So all numbers will be having 2 1s and 5 zeros. Another one weighted code is 1 out of 10 code. So as you see here, it is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the weights. So obviously for 0, I will be just putting 1 and followed by 9 zeros. Similarly for 1, second bit is 1, remaining and all 0. Similarly 2 like that. So this is what the consolidated or the summary of the codes what we had discussed. So 8421 code, 2421 code, then biquinary code, 1 out of 10 code. And then next comes the second set of codes, that is non-weighted codes. XS, the best example is XS3 code. XS3 means, as the name implies, it is XS3 plus 3. So for example, for 0, we have to write the value as 0011. That is the code for 3 in 8421. Okay. So similarly, for 8, it is 8 plus 3 is 11. So we have to write it as 1011. That is the code for 11 in 8421. Similarly, 9 is 12. So 1100. Excess 3. Just add 3 with each number, and that is the representation here. So for example, if I have 241, if I want to represent in XS3 code, for 2, I have to write 0101, and 4, it is 0111, and for 1, it is 0100. Similarly, for 758 also. Next comes is the gray code. Gray code is also another non-weighted code. It is devised by the scientist Gray. And the unique property is only 1 bit change will be there in the next adjacent digits. So here, as you see here, for one binary code, for 1 and 2, if I take means, then 0 is changed to 1 and 1 is changed to 0. So that is 2-bit change. Whereas in gray code, for 2, we have to represent it as 011, means only 1 bit change. Only the second digit or the middle digit only is changing. Remaining all is the same. So similarly, in the 4-bit code, if I want to represent 15, then it is the gray code. Let us see how to find out the code or how to convert a binary number into the gray code. It's very simple. Just I am taking the example as 10110 to the base 2. That is a binary number. I want to convert into gray code. What I have to do is this MSB we have to retain as such. Then we have to add the adjacent numbers 1 plus 0. 1 plus 0 is 1. Similarly, 0 plus 1 is 1. Then 1 plus 1 is 1. 1 plus 1 is actually 2. Then it is 1 0, that we will discard that carry 1, and only the sum we will take, that is the 0. Okay, that's what we are getting here. 1 plus 1 is 2, that is 1 0. 0 I am keeping here, 1 I am discarding. So 1 plus 0 is 1. That's how we are getting the gray code. And next type of conversion is gray to binary conversion. So for that, what we have to do is this MSB we have to retain as such, that 0. Then we have to add this 0, that is the binary number what we are getting, with the actual gray code next digit. So 0 plus 1, that is 1. Similarly, 1 and 1, here also we have to discard the carry. So we will be retaining only 0. So 0 plus 0, 0, this 0 and this 1. That is the binary result what we are getting with the next bit in the gray code. That we have to add. That is what the result. That's how we are converting the gray code to the binary. Next set of codes are alphanumeric codes. Alphanumeric codes, as we already mentioned, we have 7-bit, and it is a it represents both numbers as well as the alphabets. 7-bit code means we can have 2 power 7 possible combination, that is 128 possible codes we can have. In that, 94 graphic characters and 34 non-printable characters. 94 graphic characters includes 26 lowercase characters, 26 uppercase characters, 10 numeric digits, and 32 special characters. And the control characters are non-control character, that is non-printable characters are that backspace and this record separators. And this is what the summary of the ASCII code, that is the entire ASCII code 128 codes. So for example, here if I take this capital A, that is uppercase A, to represent that, we will be having 100, then 0001. In hexadecimal, we will just represent it as 4141. Similarly, for lowercase small a, we will be having the code as 110, then 0001. Or in hexadecimal, it is 61. Like that, we will be having the ASCII code. Next set of alphanumeric code is EBCDIC code, that is extended binary coded decimal interchange code. So it is a 8-bit code, but since we are using BCD, we will be having only 92 graphic characters and 49 non-printable characters. Again, graphic characters include 26 lowercase characters, 26 uppercase characters, and 10 numeric digits, and 30 special characters. And this is what both ASCII and EBCDIC list. Here, for example, this capital A, if I take, means it is one, ASCII means it is 1000001, as we already seen, that is 41. In case of EBCDIC, it is 11000001. So 1100 means 12, that is C, then it is 1. In hexadecimal, we can just represent it as C1. Next type of codes are, that is the third set of codes are error detecting and correcting codes. The best example is this parity code. Here we can have even parity or odd parity. Parity means actually number of ones. Here, what we will be doing is, in the information bit, if I have 3 bit, we will be adding one extra bit. That bit we call it as a parity bit. So we will make in such a way that all the codes becomes either having even parity or odd parity. That means either even number of ones or odd number of ones. For example, if I take 100, it is having only one. So I will be adding another one here as a parity bit, so that now the bit is 1001 and the total number of ones is 2. Similarly, if I have odd parity means, then I will be adding the parity bit in such a way that all numbers have only odd number of ones. Thank you.